This three-part video series reveals fundamental concerns about the calculation of global average temperature. The series details those concerns and goes on to provide a critique of the very concept of a global average temperature and its utility. Much of the fundamental concern is to do with the vast uncertainty surrounding the accuracy of the data that is recorded at climate station sites spread around the globe. This uncertainty is in direct contrast to the certainty with which the same climate data is being reported by the media and by organisations such as the United Nations and World Economic Forum. Part 1 of this series examined the claim that 2023 was the warmest year on record globally. However, an analysis of NOAA data revealed that while Africa, North America, South America, the South Hemisphere oceans and Northern Hemisphere oceans did have their warmest years recorded, that is since 1850, the Arctic, Antarctic, Asia, Europe, Oceania, which includes Australia, the Hawaiian region and the contiguous US did not experience their warmest year on record. In addition, the Antarctic has been on a cooling trend from 2001, while all these listed regions were also on recent cooling trends. This includes the entire Southern Hemisphere, which has been on a cooling trend since 2016. This prompted a further analysis to answer the question, if the Southern Hemisphere is cooling and parts of the Northern Hemisphere are cooling, what is warming? In brief, we found that the continents of North America and Australia, as part of Oceania, were cooling, and the Antarctic region that includes the continent of Antarctica was also cooling. Africa was barely warming, while South America, Europe and Asia were on warming trends, with the strongest trends belonging to Europe and Asia. The concise results of part 1 of this series can therefore be stated as: very large regions and continents of the globe did not record their respective warmest year on record during 2023. Very large regions and continents of the globe have in fact been on cooling trends since at least 2016, and the entire Southern Hemisphere remains on a cooling trend from 2016 to 2023. We are now ready to start part 2, which is centred around issues that bring out the themes of certainty and uncertainty in the concept of a global average temperature and the practical difficulties that contribute to its uncertainty. In 2013, the IPCC stated, "Science always involves uncertainties. These arise at each step of the scientific method, in the development of models or hypotheses, in measurements, and in analysis and interpretation of scientific assumptions." Climate science is no different. The question is just how much uncertainty is acceptable in the calculation of global average temperature. How much uncertainty is acceptable when enormous decisions regarding net zero and the UN 2030 agenda require high levels of certainty and data integrity? There is therefore great danger in the attitudes of the World Economic Forum and the United Nations when, in 2019, they signed the Strategic Partnership Framework, and in 2023 when the United Nations Secretary General made his global boiling statement. The heads of these global organisations and their actions project only certainty, with no room for doubt. Part 2, however, introduces considerable uncertainty when it analyses these potential lines of inquiry that were generated as a consequence of Part 1. Why are the annual average temperatures and trend rates of the Northern Hemisphere different to those of the Southern Hemisphere? Could it be that the growth in populations, especially in the Northern Hemisphere, has, in and of itself, produced an increase in temperature that is independent of increases in greenhouse gas atmospheric concentrations? Could it be that the increase in urban populations, especially in the Northern Hemisphere, and the resultant UHI effect has resulted in inappropriate weather station sites, and thus incompatible data? We finish with a summary of the analysis and then a brief preview of Part 3 of this series. The first question posed is, why are the annual average temperatures and trend rates of the Northern Hemisphere different to those of the Southern Hemisphere? The answers will lead to a very important point related to the calculation of global average temperature. First, the facts. From the beginning of modern record keeping, 1850, up to 2023 inclusive, the globe has warmed at a trend rate of 0.57 degrees Celsius per century. Over the same period, the Southern Hemisphere has warmed at a rate of 0.44 degrees Celsius per century. And over that same period, the Northern Hemisphere has warmed at a trend rate of 0.7 degrees Celsius per century. This is 59% greater than the trend rate of the Southern Hemisphere. What are the potential reasons behind this disparity? One reason is that the Northern Hemisphere receives a different variation of the Sun's energy to that received by the Southern Hemisphere. Why is this? It is because of the Earth's orientation to the Sun. Earth is not oriented vertically north to south. Instead, it is tilted on its axis. This is known as its axial tilt or obliquity. The tilt varies and swings back and forth between 22.1 and 24.5 degrees over a period of about 40,000 years for the complete cycle. This tilt alone ensures a different and varying distribution of the Sun's energy output across the Earth's hemispheres. But there is another factor to consider. The Earth wobbles along its rotational axis. This is known as precession. The complete cycle of axial precession spans about 26,000 years. Obliquity and precession thus combine to vary the amount of the Sun's energy received by each hemisphere. There are, of course, many other factors to consider, but the final point we cover is that of the short timescale set of motions in the precessional cycle as it goes through its long-term cycle. The long-term cycle seems to be one of a smooth mathematical sweep of the stars, but it is not that simple. This long-term motion is driven by the gravity of the Moon and the Sun acting on the Earth's equatorial bulge. But because the Moon orbits the Earth once a month in a tilted elliptical orbit, the Earth's spin axis also undergoes a smaller set of motions on much shorter timescales. These irregular motions can occur over days to years. The combination of the Earth's constant but varying tilt plus the short-term and long-term variation of the Earth's axial precession ensure that the Northern and Southern Hemispheres cannot be regarded as equal in terms of the energy they receive from the Sun. There are other very significant differences. The Southern Hemisphere surface is covered by around 20% landmass and 80% water. The Northern Hemisphere surface is covered by around 40% landmass and 60% water. The Southern Hemisphere is home to about 10% of the human population, while the Northern Hemisphere is home to about 90% of the human population. Based on this information, a brief summary is provided in answer to the question, why are the annual average temperatures and trend rates of the Northern Hemisphere different to those of the Southern Hemisphere? Because the Earth is tilted on its axis and the effects of the precession wobble, the Northern Hemisphere is in receipt of differing levels of the Sun's energy to that received by the Southern Hemisphere. In addition, the Northern Hemisphere's structure is radically different to that of the Southern Hemisphere in terms of land and ocean coverage and in the proportions of human population. Because of these differences, a final very important point that will feature strongly in part 3 of this series, neither the Northern Hemisphere nor the Southern Hemisphere can be regarded as an exact half of planet Earth. The next line of inquiry picks up the theme of populations. It asks, could it be that the growth in populations, especially in the Northern Hemisphere, has, in and of itself, produced an increase in temperature that is independent of increases in greenhouse gas atmospheric concentrations? The increase in local temperatures as urban populations grow is known as the urban heat island effect. The effect is nicely summarized in this 2016 paper. Urban heat island (UHI) effect is widely recognized as a heat accumulation phenomenon, which is the most obvious characteristic of urban climate caused by urban construction and human being activities. The IPCC recognizes UHI and in its 2013 report stated that it is indisputable that UHI and land use, land cover are real influences on raw temperature measurements. We will return to the stance of the IPCC a little later, but for now we will relate UHI to the analysis we have completed to date and introduce population size, growth and density. Our analysis has shown the two continents with high positive trend rates in annual temperature were Asia and Europe. How does that compare to population sizes? From this chart we see that Asia has the world's largest population, while Europe is third largest, with Africa possessing the second largest population. If the urban heat island effect were directly related to population, it would be expected that Africa would be warming more than Europe, but Africa only barely warmed from 2016 to 2023. Africa, however, is much larger than Europe. Could it be the density of population, that is the number of people per square kilometre, that is the governing factor? If we take this data from 2021, that gives the land area of each continent together with population size, we find Asia has the highest population density and Europe comes second to Asia, with a density significantly higher than Africa. In fact, both continents have a population density greater than that of the Earth. There is thus a good correlation between population density, UHI and annual temperature increases. If we take one step further, we see that the population density of the Northern Hemisphere is almost 5 times greater than that of the Southern Hemisphere. And as the Northern Hemisphere is warming significantly more than the Southern Hemisphere, we again have correlation between population densities and warming trends. Going back to the original question, what role does the rate of growth in population play? We can look at some examples of cities from Asia, Europe, and the continent of Oceania. First, Asia. Beijing population has grown from 1.671 million in 1950 to 21.76 million in 2023 at a linear trend rate of over 2.5 million people per decade. Delhi population has grown from 1.369 million in 1950 to 32.941 million in 2023 at a linear rate of over 4.2 million people per decade. In Europe, the Paris population has grown from 6.283 million in 1950 to 11.208 million in 2023 at a linear rate of over 622,000 people per decade. And in Oceania, Sydney, Australia, the population has grown from 1.69 million in 1950 to 5.121 million in 2023 at a linear rate of over 421,000 people per decade. There is therefore a correlation between high rate of population growth in Asia and a high trend in annual temperature growth in Asia. Not quite so high a rate of population growth in Europe, with not quite so high a trend in annual temperature growth. A relatively low rate of population growth in Oceania, with a relatively low trend in annual temperature growth. This analysis is of course at a high level with a small sample of locales, but there does appear to be a correlation between the growth in population and growth in annual temperature. To evaluate whether such increases in temperature are significant and independent of increases in greenhouse gases, atmospheric concentrations, we turn to the paper by Feinberg. Published 2020, this paper contains much that is relevant to our topic. Rather than paraphrase, we will walk through direct quotes of some of the pertinent statements. One key paper often referred to is McKittrick and Michaels, who found in 2004 and 2007, using regression trends on socio-economic, geographical and temperature indicators, that the net warming bias at the global level may explain as much as half the observed land-based warming. Another independent study by Delat and Moraes, 2006, found very similar results. In 2007, IPCC questioned these findings, stating the locations of greatest socio-economic development are also those that have been most warmed by atmospheric circulation changes, which exhibit large-scale coherence. However, in 2010, McKittrick responded to the IPCC statement with two publications. The first, entitled "Atmospheric Oscillations Do Not Explain the Temperature Industrialization Correlation." The second, by McKittrick et al. In 2010, detailed that evidence for contamination of climatic data is robust across numerous datasets. Consequently, we conclude that important data products used for the analysis of climate change over global land surfaces may be contaminated with socio-economic patterns related to urbanization and other socio-economic processes. A little later, the IPCC modified its position on the urban heat island effect. It stated that it is indisputable that UHI and land use, land cover are real influences on raw temperature measurements. At question is the extent to which they remain in the global products. Regarding that point, Feinberg paper goes on to quote authors that have determined the extent of the UHI effect. For example, Zhao and Zhuang et al. Found that UHIs contribute to warming in China by about 30%. Bun et al. In China at Shijiazhuang Station for periods 1965 to 2012 found the urban-rural land surface temperatures (LST) trends correlated 100% to urbanization contributions, indicating the yearly increase in annual mean LST at the urban station is entirely caused by urbanization. Entirely caused by urbanization. They were independent of greenhouse gas atmospheric concentrations. The Feinberg paper goes on to warn that the scale and intensity of the UHI effect will be increasingly serious with the ongoing urbanization. It points out studies of UHI effect of Szeged and New York are 3.1 degrees Celsius and 8 degrees Celsius respectively. Meanwhile, Feinberg says it is found that China is also experiencing severe UHI effect in many modern cities, especially the average temperature difference on the outskirts of Beijing reaching 3.3 degrees Celsius from 1961 to 2000. And the UHI effect of Shanghai reaches 7.4 degrees Celsius. It concludes that these studies use land-based temperature station data to make assessments. In other words, they are not theoretical. The data has been obtained from the weather station sites in urban areas. The stark conclusion was and is that the true impact of rising atmospheric CO2 on the global climate may well be vastly overstated. A concise summary. In 2013, the IPCC recognized the UHI effect. The Feinberg paper concluded that as a result of the UHI effect, the true impact of rising atmospheric CO2 on the global climate may well be vastly overstated. So, the answer to this question is yes, the growth in populations, especially in the Northern Hemisphere, has, in and of itself, produced an increase in temperature that is independent of increases in greenhouse gas atmospheric concentration. This, again, raises the question of just how much uncertainty is acceptable in the calculation of global average temperature. And how much uncertainty is acceptable when enormous decisions are in the balance regarding net zero and the UN 2030 agenda. The next line of inquiry. Could it be that the increase in urban populations, especially in the Northern Hemisphere, and the resultant UHI effect has resulted in inappropriate weather station sites? Some brief information on the meaning of inappropriate weather station sites. The World Meteorological Organization has defined standards for weather station sites. This is because, as they say, temperature is one of the meteorological quantities whose measurements are particularly sensitive to exposure. For climate studies in particular, temperature measurements are affected by the state of the surroundings, by vegetation, sources of heat like buildings and other objects, by ground cover, etc. The most appropriate site for the measurements is, therefore, over level ground, freely exposed to sunshine and wind and not shielded by or close to trees, buildings and other obstructions. It notes that in towns and cities, local peculiarities are expected to be more marked than in rural districts. In other words, it is more difficult in urban areas to find appropriate sites. The NOAA National Weather Service adds that a level, open clearing is desirable so the thermometers are freely ventilated by airflow and the sensor should be at least 100 feet from any paved or concrete surface. This is an example of a weather station protected by a Stevenson screen. The stipulation of being at least 100 feet from any paved or concrete surface would be very difficult to comply with in large crowded cities such as Delhi. It would have become increasingly difficult over the period 1950 to 2023 as the population of Delhi grew and population density increased from 923 people per square kilometre to 22,212 people per square kilometre. This growth brings us to a related issue. A crude diagram will help explain. The black line encloses the area of Delhi. In 1950, we can imagine a number of weather station sites within urban Delhi. The exact number is not relevant for our purposes, but we can use the UK as a rough guide. The UK land area is just over 244,000 square kilometres. The approximate number of UK weather stations is 350. That's about one station per 700 square kilometres. The Delhi land area is 1,483 square kilometres. So the approximate number of weather stations in Delhi would be 2. If we now look at the square kilometre in which the station is sited, we can see that in 1950 around 923 people would have been located in that square kilometre. By 2023, there would have been around 22,000 people in that same square kilometre. Given this population density growth, is it conceivable that an appropriately sited weather station in 1950 was in 2023 still at least 100 feet from any paved or concrete surface? Or that the site is appropriate in that it is over level ground, freely exposed to sunshine and wind, and not shielded by or close to trees, buildings, and other obstructions. This exposes a dilemma regarding the calculation of global warming. If the Delhi weather station sites today are the same as they were in 1950, then it is extremely unlikely they are appropriate. This is directly due to the urban population growth and the UHI effect. However, if the Delhi weather station sites of 1950 have been moved, then further issues surface. Such issues are concisely summarised by NOAA National Weather Service. Station moves where the new equipment location is within 5 miles of the original site and the difference in elevation is 100 feet or less are also assumed to be incompatible unless they pass a data compatibility evaluation. Thus, if the move is incompatible, then the data from the new site cannot be compared to the data of the old site. This is a very significant issue as most relocations are expected to exhibit data incompatibility. Although our discussion has been, if you like, theoretical to date, here are 2 real-world practical examples of inappropriate weather station sites. Such pictures and detailed criticism of weather station site locations are appearing more and more in the media. This example has one very relevant and deeply troubling headline stating that 1/3 of UK Met Office temperature stations may be wrong by up to 5 degrees Celsius. The information was obtained as a result of a Freedom of Information request. The detailed background to the inquiry is provided by the WMO. It points out that the environmental conditions of a site may influence measurement results. Therefore, these conditions must be carefully analysed, in addition to assessing characteristics of the instrument itself, so as to avoid distorting the measurement results and affecting their representativeness, particularly when a site is representing a large area. Weather station sites are judged by WMO to be in one of 5 classes. Classes 1 and 2 are deemed appropriate. Classes 3 to 5 have various degrees of uncertainty, ranging from 1 degree Celsius to 5 degrees Celsius. The WMO emphasises that a Class 1 site can be considered a reference site. A Class 5 site is a site where nearby obstacles create an inappropriate environment for a meteorological measurement that is intended to be representative of a wide area, at least tens of square kilometres. We now look at the results for the UK sites coming out of the Freedom of Information request. Only 6.3% of the weather station sites can be classed as reference sites, and just another 7.4% have no uncertainty associated with them. 8.4% have an uncertainty of up to 1 degree Celsius. 48.7%, that's just about a half of all UK weather station sites, have an uncertainty of up to 2 degrees Celsius, and an almost unbelievable 29.2%, nearly a third of all UK weather station sites, have an uncertainty of up to 5 degrees Celsius. It is difficult not to agree with the conclusion in the article that on no scientific basis should these figures be used for the promotion of the net zero project. This rather tepid statement by the WMO does not really remove the doubt about the accuracy of the figures derived from inappropriate sites. WMO says that in a perfect world, all sites would be in Class 1, but the real world is not perfect, and some compromises are necessary. It seems a very large compromise to accept 29.2% of Class 5 sites and 48.7% of Class 4 sites, giving a total of 77.9% of UK weather station sites that have inappropriate uncertainty classifications. Going back to the position adopted by the WMO, there can be little doubt that the organisation is fully aware that the increase in urban populations has resulted in inappropriate weather station sites, for it recommends that the rating of each site should be reviewed periodically as environmental circumstances can change over a period of time. A systematic yearly visual check is recommended. If some aspects of the environment have changed, a new classification process is necessary, and a complete update of the site classes should be done at least every 5 years. Therefore, this line of inquiry is confirmed. The increase in urban populations, especially in the Northern Hemisphere, and the resultant UHI effect has resulted in inappropriate weather station sites. A final important point. Although the United Kingdom has been singled out as an example, the problem is a global problem. According to the World Bank Group, globally, over 50% of the population lives in urban areas today. By 2045, the world's urban population will increase by 50% to 6 billion. it warns that city leaders must move quickly to plan for growth. And it must follow that climate organisations around the globe must move just as quickly to plan for and implement appropriate weather station sites and relocations. With that observation, now is the time to summarise the lines of inquiry contained in part 2 of this series. The first line of inquiry investigated why are the annual average temperatures and trend rates of the Northern Hemisphere different to those of the Southern Hemisphere. There are numerous quite fundamental and well-known reasons. The most obvious, but at the same time the most ignored difference, is that the Northern and Southern Hemispheres are very, very different. They are different in land coverage, ocean coverage, human population coverage, and human population density. In addition, the combination of the Earth's obliquity and precession ensures that each hemisphere receives differing intensities of solar radiation, known as insolation. As this study states, the structure of the latitudinal and seasonal distribution of insolation depends upon the precessional parameter and the obliquity. And just to clarify one thing, yes, it does take thousands of years for the tilt to move from one extreme to the other and back again. But the Earth is always tilted. It is just a question of by how much. As a result of all these factors, neither the Northern Hemisphere nor the Southern Hemisphere can be regarded as an exact half of planet Earth. And the two hemispheres are certainly not equal. The importance of this will be referenced a little later. The next line of inquiry. Could it be that the growth in populations, especially in the Northern Hemisphere, has, in and of itself, produced an increase in temperature that is independent of increases in greenhouse gas atmospheric concentrations? When confronted with these surges in populations, it seems just common sense to infer that of course temperatures would have gone up in such urban areas just simply by the hustle and bustle of ordinary everyday life. Which is another way of saying, as does this study, that the UHI effect is the most obvious characteristic of urban climate caused by urban construction and human being activities. It is stressed that the IPCC recognises UHI and its real influence on raw temperature measurements. And the effect of UHI on temperature measurements may well be that the true impact of rising CO2 on the global climate is being vastly overstated. Inquiry 3. Could it be that the increase in urban populations, especially in the Northern Hemisphere, and the resultant UHI effect has resulted in inappropriate weather station sites and incompatible data? The reality of this risk is recognised by the WMO and its classification of sites. But the practical difficulties of site relocation due to the increase in population and population density has resulted in this potential margin of error. And in fact, this margin, 86.3% of UK weather station sites have WMO recognised uncertainties. And put quite simply, they are probably wrong. There is of course an enormous, staggering catch-22 logic governing this situation. Such inappropriate sites need to be moved to appropriate locations. But most relocations are expected to exhibit data incompatibility. All of this, and there is more to come in part 3 of this series, forces the conclusion that there is too much uncertainty in the measurement of global average temperature, and that, given the day-to-day practical organisational problems of inappropriate weather station sites and the associated issues of urban population growth and UHI, there must be immense problems and uncertainty when comparing the global average temperature of one year to the global average temperature of another year, comparing 2023 to 1950, for example. There must be even greater uncertainty when carrying out the measurement of global warming, which the IPCC defines as being relative to the period 1850 to 1900, when the population of the world grew from around 1.2 billion in 1850 to around 1.6 billion in 1900. 1.6 billion is just 1/5 of the 2023 population of 8 billion. It is accepted that, of course, science always involves uncertainties, and governments and organisations cannot always be certain. Sometimes they do need to make decisions when there is an element of uncertainty. However, the depth of uncertainty uncovered in this video is not acceptable. This level of uncertainty warrants a move from the present certain plans of the net zero and the UN 2030 agenda to a more considered, cautious and balanced approach. That concludes part 2 of this series. And now just a brief preview of part 3, which again goes into the issue of how much uncertainty is acceptable. The major topic will be to critique the very concept of a global average temperature. Regarding uncertainty, we return to the uncertainty involved when comparing the global average temperature of one period to the global average temperature of another period. This is very pertinent as the IPCC measures global warming by comparing a selected 30-year period to the period 1850 to 1900. A couple of the themes will be data incompatibility, especially when there were fewer weather stations 1850 to 1900 than there are now. It is also asked, why is the period 1850 to 1900 being used as the baseline to calculate global average temperature? The science behind this decision is questioned. As to the concept of a global average temperature, a Gedanken experiment will explore this line of inquiry. Could it be that the very concept of a global average temperature is significantly flawed, lacks meaning, is dangerously misleading, and urgently needs to be re-evaluated? If you appreciated this video, please like and subscribe. You are also invited to join our community on locals.com. You can click on the button below to connect directly with our locals.com website. You may also be interested in this video, released some time ago.